All right, let's dive into something that feels like it's been pulled straight from a sci-fi movie, but is actually happening in labs right now. We're talking about quantum teleportation. And trust me, the reality is way cooler than the fiction. I mean, when you hear the word teleportation, your mind probably jumps right to Star Trek, doesn't it? Beam me up, Scatty! That whole idea of dissolving into a cloud of glitter and reappearing somewhere else. But is any of that real? Can we actually do it? Well, here's the thing. The answer is kind of yes and no. Real teleportation is a thing, but it's not about beaming people across the galaxy. Nope, it's about something way, way smaller. And honestly, the real science behind it is so much more mind-bending and fascinating than anything Hollywood has dreamed up.
Okay, so to get our heads around this, we have to forget about people for a second. We need to start with a single, fundamental particle of the universe.
And that particle is called a photon. So what's a photon? Simply put, it's a single, tiny particle of light, the absolute smallest packet of light you can possibly have. Think of it as just one little piece of a sunbeam. Now here's where it gets really interesting. Every single one of these photons carries a little secret with it. It's a special property called polarization, and that secret, that's the piece of information that scientists actually want to teleport. So what on earth is polarization? Well, Bill Wootters, one of the guys who actually co-invented this whole process, gave us the perfect analogy. Just think about your polarized sunglasses. You know how they work, right? They let in light that's going up and down, that's vertical, but they block all that annoying horizontal glare bouncing off the road. A photon is kind of like that. It can have a vertical state or it can have a horizontal state. And that specific state, that is its secret. So that brings us to the big challenge. Let's imagine we have two people. We'll call them Alice and Bob. Alice has a photon, and she knows its secret state. How in the world does she get that exact information over to Bob, who might be miles and miles away? Now you might be thinking, easy, just look at it and call Bob up. If only it were that simple. You see, the quantum world, it plays by some really, really strange rules, and those rules make this whole thing incredibly tricky. There are two fundamental can't-dos in quantum mechanics that get in the way. First, you just can't measure the photon to figure out its secret. The very act of observing it, of trying to peek at its state, will instantly change or even completely destroy that original state. Poof, it's gone. And second, you can't just make a copy of it. The laws of physics literally forbid you from creating a perfect clone of a quantum state. So you're in a real bind, right? You can't look at the secret without ruining it, and you can't make a duplicate to send over. It seems completely impossible. So if you can't measure it and you can't copy it, what's the trick? How do they do it? Well, the solution is just brilliantly weird. It's one of the coolest ideas in all of physics, and it all comes down to a secret ingredient, a special resource that Alice and Bob have to prepare ahead of time. This special quantum resource, as Bill Wootters calls it, is the real magic trick. It's a pair of particles that are entangled. Now, entanglement is, well, it's wild. It's this spooky, invisible connection between two particles. It means that whatever happens to one of them instantly affects the other one, no matter how far apart they are. We're talking opposite sides of the universe, and the connection is still instantaneous. And this is so important to understand. For this to even have a chance of working, Alice and Bob had to have met up sometime in the past. Back then, they created this entangled pair and each took one particle. Then they could go their separate ways, move to different cities, different countries, whatever. But now, in the present, they each still hold their half of that original shared resource. Okay, so they each have their special particle. What happens now? This brings us to the biggest, most important takeaway of this whole thing. This is the part that separates the sci-fi fantasy from the mind-blowing scientific fact. Just listen to this quote from Bill Wootters himself. It never actually traverses the intervening space. Let that sink in for a second. The information, that photon secret, it doesn't travel through the space between Alice and Bob. It doesn't fly through the air, it doesn't go down a fiber optic cable. It just disappears from one place and reappears in the other. So let's break this down, myth versus reality. The sci-fi myth is all about moving matter, taking apart a person's atoms and rebuilding them somewhere else. But the scientific reality, it's all about moving information. Alice's original photon is actually destroyed in the process, but its exact state, its secret information, is instantly imprinted onto the photon that Bob already has with him. So here it is, the absolute bottom line. The one thing to remember from all of this: quantum teleportation is not the movement of matter. It is the perfect, instantaneous transfer of information about the state of that matter from one location to another. You're not sending the photon, you're sending its secret.
And that leaves us with this incredible, mind-bending thought, doesn't it? This isn't really about travel. It's about a whole new way to communicate. If information doesn't even need to travel through space to get from point A to point B, what could that mean for the future? We're talking about things like unhackable computer networks, incredibly powerful quantum computers, and a future of communication that we can barely even begin to imagine.